Okay, we're back again for another lesson in the chapter on chemical bonding and reactions. To give a quick recap, in one of our earlier lessons we talked about ionic bonding as the type of bonding that involves electrostatic attraction between oppositely charged ions, a cation and an anion, where each of those species has either gained or lost electrons in order to achieve the magic number of electrons, and then once they become ions, we have electrostatic attraction between them to form what we call an ionic bond. We briefly talked about metallic bonding, which applies to metals and helps us explain a number of the properties of metals, and that involves electrons being able to hop around in the lattice of a solid. Then in the last lesson we talked about covalent bonding, which is a type of bonding in which electron pairs of electrons are shared between atoms, and especially the elements in the upper right hand corner of the periodic table, carbon, nitrogen, oxygen, and also hydrogen, play covalent chemistry very well. They know how to share. They know how to share toys. In this case, sharing electrons to form either single bonds or double bonds or even triple bonds in some cases. And in doing so, they satisfy the octet rule by sharing rather than one element completely grabbing the electrons from the other. Although we saw that oxygen tends to not share as well, leading to what are called polar covalent bonds. In this lesson, we're going to continue talking about covalent chemistry, and especially we're going to focus on the chemistry of carbon, an entire field called organic chemistry. And we're going to be brief, a large topic, and in fact there are students majoring in many areas of science will take a full year of coursework in organic chemistry, and they'll tell you it's one of the most enjoyable years of their life. Chemistry of carbon, or what we call organic chemistry. Well, first of all, let's point out that carbon is fairly abundant, and it's also near the top of the periodic table, and it's an important player. It is the fourth most abundant element in the universe by mass. It's the 15th most abundant element on planet Earth, and in terms of living system, it's the second most abundant element after oxygen. And it's present in all life forms, and in fact the name organic chemistry derives from the fact that all living systems seem to be based on the chemistry of carbon. That is, all the important molecules in living systems involve carbon. Now, carbon plays this key role because it prefers covalent bonding, and as we'll see in a second, that covalent bonding can lead to the production of very long molecules and a number of different functional, what we call functional groups, molecules that have different properties. There's a broad range of organic compounds that can be formed, and we're only going to show you a few examples. And in particular, I note that carbon enables the formation of very long chains, which leads to polymers, which we'll focus on a little bit. In the bottom left-hand corner of this slide, I show one of the simplest organic molecules involving carbon, which has formed 4 covalent bonds to 4 different hydrogens. And if you look at the right-hand part of this graphic, you'll see the simplest way that we draw carbon with 4 dashes to 4 hydrogens. Each of these dashes, just to recap what we talked about last time, each of these dashes involves a pair of electrons, one coming from the hydrogen, one coming from the carbon, to form each of those bonds. So this very simple organic molecule with carbon in the middle is called methane. Now there are a large number of molecules that can be formed in this way. I've shown here just 2 examples. One is the amino acid serine, and the other is glucose. Well, you probably have heard of glucose, maybe not of serine. But as you can see, carbon tends to be able to link to other carbons and to hydrogens and to nitrogens and to oxygens with either single bonds or double bonds, and as a consequence can build up quite elaborate molecules. This is almost like putting together Tinker Toys. In fact, it just kind of reminds me of that because I played with Tinker Toys, and they probably don't sell Tinker Toys anymore. They're much more into Legos nowadays. Here are a couple of interesting organic molecules. The top half of the slide shows benzene. Now, you may have heard of benzene because it's a fairly common organic solvent. Benzene has a cyclic structure with 6 carbons linked together to form a ring. Each of the carbons also is bonded to one hydrogen, so it's a nice symmetric looking molecule. Now, the ring structure, which also includes alternating double bonds between carbons, if you look at the second structure you can see what I mean by alternating double bonds, gives benzene certain characteristics. It gives benzene a degree of stability, an added degree of stability, which turns out to be important. Now, I show different representations of benzene because organic chemists sometimes get tired of drawing all of the atoms, and so sometimes they'll just take shortcuts and not draw the hydrogens atoms where they should be because they're sort of understood. So the third drawing shows a very simple representation just showing the ring structure, and in fact the carbons are admitted as well as the hydrogen atoms. And then at the right I show a space-filling depiction of the molecule benzene to show you a little bit more about what it actually looks like. And the bottom half is a molecule called choranine, which sometimes is called superbenzene, where you see these 6-membered rings, actually 6 of them linked together, and actually in doing so it forms another ring in the middle. And the right side shows the space-filling diagram for choranine, which sort of looks like a whoopee cushion, I guess. This slide shows different forms of pure carbon. Now, I show this because it's pure carbon, it's element carbon, but the carbon atoms are actually bonded to other carbon atoms in different ways in these different forms of carbon. This leads to what we call allotropes of carbon. The one on the left is the one that you're most familiar with. It's graphite or charcoal, and as you can see, of course, it looks like a lump of coal, but the molecular structure of graphite is one in which there are flat sheets or planes of carbon atoms that are bonded to other carbon atoms. Now, if you have a lead pencil, I'm sure you have a lead pencil, first of all you need to realize that it's not lead. You've just been told that it's lead. It's not lead. It's actually graphite. It's a graphite pencil. The lead pencil works because graphite is so soft that when you rub it against a piece of paper, you can sort of rub off a film of graphite onto the paper. And that's because in graphite, the carbon exists in these sheet structures which can easily slide past one another and can be rubbed off onto the sheet of paper. That is, it's a very soft form of carbon. By contrast, diamond is one of the hardest substances known. It is another allotrope of carbon, but if you look at the blow-up of what the molecular structure of diamond looks like, you can see that it's quite a bit different. Here, each individual dot is a carbon atom, and each carbon atom is bonded to 4 other carbon atoms in a network structure that makes the diamond very, very strong. That is, you can't easily cut diamond because doing so would require cutting a great number of bonds. The bottom right corner shows 2 relatively newly discovered allotropes of carbon. One is called fullerenes and the other is called nanotubes. The fullerenes are spherical molecules. In the most common form, there are 60 carbon atoms linked together to form this very nice looking spherical ball. It looks very much like the traditional soccer ball. It's called fullerenes in reference to Richard Buckminster Fuller, the architect who designed geodesic domes. The one on the right is called a nanotube, where carbon can form this cylinder that can extend on and on to form a long tube. Now, these 2 allotropes, or these 2 forms of carbon, were discovered only 20 or 30 years ago, and there's quite a bit of interest in these nowadays in a field called nanotechnology, because There's interest in the strength of the nanotubes, for example, the ability to conduct electricity, the ability to entrap various molecules inside the tubes, or the spherical fullerenes. We'll talk a little bit more about some of these later on. We're going to pause now for another quick break, and then we'll come back and we'll talk about polymer chemistry.